May, may I first start by introducing Daniel Gowland, who is on the screen and who, can you give a wave down, Daniel? That's it. And Daniel is the winner of our John and Anne Phillips Prize. Not mapping this year, but Daniel has submitted a project as part of his final year undergraduate work at Hull. And the title of it, he produced a poster, which was considered by far the best. And the poster is about the potential of utilizing abandoned coal mines across the Northeast for low enthalpy geothermal heating. So a good relationship with the talk we have this evening. And that we hope that poster will be available for view. If not in the near future, we hope that'll be available at at the Geologists Association meeting, which is in September. So our speaker tonight is Dr. David Peacock, who started as a doctoral student at the University of Southampton and worked in universities for a while until going into commercial world with in Dutch and Norwegian hydrocarbon firms analyzing the Earth's subsurface geology. He then moved to academia at Bergen, Göttingen, and now at Hull. And his main interests are the fault and fracture analysis and the practical applications of structural geology in geothermal energy and radioactive waste storage, both of which are major things here. So the idea that the Humber will lead the UK's green energy transition. So Dr. Peacock is talking on geothermal potential mapping of the Sherwood Sandstone in the Humber region. Thank you, David.
Well, thank you very much. I'm just going to get the presentation started. Here we go. Can you see the screen okay?
Fine. Yes.
Okay, good. So well, thank you very much for inviting me to speak to you, and as a virtual presentation. One thing is, if people have interest in this, they're very welcome to contact me. I'll give an email address at the end that should be a permanent email address, and hopefully that this presentation could be made available to people. So what I'm talking about here is the geothermal potential of the Sherwood Sandstone, and particularly about mapping that potential. I'll just point out a couple of things. My colleagues at the University of Hull, Professor Mark Anderson, and Dr. Eddie Dempsey, they're collaborators on this project. And if you notice down the bottom corner here, the Northern Net Zero Accelerator, they funded this work. There's a lot of interest in the northeast of England for decarbonisation and for as a stimulus for economic growth. And one of the aspects is geothermal energy. So I'll show you the end of it, really, in a way. That this is the favourability map. This is the final favourability map that's been produced. A few things to notice about it. The study area goes from just north of Flamborough Head in the north to the south. I can't remember the name of the town down here. It goes down into Lincolnshire, and then Doncaster somewhere over here. I'll show a map with the exact geography on it. But what this map shows is, you notice these are very pixelated. These pixels represent favorability in a kilometre square grid. And so what I've done is collected a range of different data types and merged them to produce what's a favorability, what would be a geothermal favorability map. And the red colours are high favorability, the greens and the blues are a lower favorability. So the presentation here is about why we're doing this, how we get to this map, and what it means. So the contents of the talk here, so some of them are about sort of the background, what geothermal energy is, why you look at the Humber region, about the project, some of the geology, and then to some of the technical aspects of how we identify the best places for geothermal energy, what the results are, and what the results mean. The conclusions are I'll frame the conclusions in terms of these four questions. So why does the Humber region need geothermal energy? Might geothermal energy work in the Humber region? Can we identify the best places for geothermal energy? And what could geothermal energy achieve? So these are four questions that I'll try and answer at the end. So, oh yes, so I thought what I'd do is put in this presentation three exciting images showing things that people know, that associate with geology. So the first one is this, a volcano. It's an exciting picture. People think volcanoes are very exciting. There is a reason for showing this, and it's an illustration that the Earth is hot. So as you go deeper in the Earth, the rocks become hotter, and they can become so hot that they melt. And when those molten rocks reach the surface, they form volcanoes. So obviously, there's no volcanoes in the Humber region, and people tend to associate geothermal energy with things like this, which is in Iceland, a volcanic area where the rocks are quite hot. You don't have to drill down deeply to get very hot rocks. You can extract the water and you can power steam turbines and generate electricity, which is fantastic because the electricity that you generate can be put through cables and people can use it in other places. Now, the rocks near the surface in the Humber region are not that hot, so you need a different approach. So the simple geothermal system would look something like this: that you have one borehole down into an aquifer, and you extract hot water or warm water. You run it through a heat pump, and then pump the water back down into the ground, and you create this loop of water that's getting hotter. It's extracted, you put it through a heat pump, and then you pump it back in, and the heat you then use in a district heating network. You might have something like a power station or factories. You might have a geothermal system, and you're creating hot water, which you're then pumping through pipes to different buildings, to factories, to hospitals, schools, universities, libraries, that sort of thing. Could be residential buildings. You wouldn't tend to bother putting a district heating network connecting individual houses, but it would be a sort of a local network of hot water that's pumped through a series of buildings. So it would work well for a hospital or a university. So one thing I should mention here, I'll be showing some cross sections, and for those people that are not familiar with the cross section, it's if you imagine a kind of slice through the Earth, that you have a line on the Earth's surface, in this case going from the southwest to the northeast, and then so on the x-axis it's a distance, and on the y-axis it's depth, and it's a representation of what the rocks do at depth. And the reason I'm showing this one is because it's showing some oil fields, and oil and gas are interesting things because when you extract them, you could then transport them somewhere else to be used, which makes life relatively simple. But once it's extracted, it's gone. It's a non-renewable resource. Another issue with oil and gas is pollution. It's a dirty industry. You tend to get a lot of pollution. Well, if you're unfortunate, you get oil slicks like this. And perhaps more importantly, you get this sort of pollution, which is not visible pollution, which is CO2 and methane and other gases which contribute to global warming. And the recent heat wave in Britain, the droughts indicating climate change and the need to decarbonise. So we should be moving away from oil and gas to renewable resources like geothermal, like solar, wind, tidal, sorts of renewable energy. Why specifically the Humber region? Well, it is a major industrial centre. This is the Saltend Chemical Park, big factories, chemical factories. There's shipping, there's oil refineries, gas terminals, various hospitals, universities. There's a big demand for energy in this region. I was actually very surprised to learn that the Humber as a region, it produces about 50% more CO2 than the next largest industrial cluster. I didn't realize it was that important. I'm not from that area, so I didn't really realize how important it was. But there's a need to achieve net zero. But there is an opportunity because there's this sedimentary basin beneath East Yorkshire and North Lincolnshire, and it contains geothermal energy, which hasn't properly been developed yet. There's big advantages to geothermal energy. It creates a permanent base load of energy. So it's unlike solar and wind power, which are intermittent. And I know people that are opposed to renewables point at wind and solar and say, oh, what happens when it's not sunny and when the wind stops blowing? Well, geothermal doesn't have that problem. It's a local energy source. So you're taking heat out of an area and you're using it, you're consuming it within that area. It's a local energy source. And it's also versatile. You can use it for a range of industrial processes of heating hospitals and other buildings and district heating. It's a range of processes that it can be used for. So what this project is, it's called the Huge Project, which stands for Humber Geothermal Energy, I believe. And it aims to provide information and develop methods that will help people understand issues, risks, and opportunities. And we're aiming at not just geologists, but engineers, decision makers, politicians, and the public. So it's to make things that people would understand. One thing as well is if you have suggestions, if for example I've glossed over things you think I shouldn't gloss over or explain things poorly, then please let me know, because an aim is to make this understandable for people. So I'd So there are three work packages as part of the project, and the focus of this presentation is work package one, which is to determine and de-risk the geothermal potential of the Humber region. I'll point out as well that we have project partners, Eden Geothermal, who have been involved in the Eden project in Cornwall, and Consortium Drilling, who are one of the leading geothermal drilling companies. So what I'll be talking about here for the next few slides are this qualitative assessment of the potential reservoirs. We focused on the Sherwood Sandstone, but I'll explain why the Sherwood Sandstone. I'll be presenting the geothermal favorability mapping and presenting some simple work I did on the economics and environmental impact. So the geology. So the Earth gets hotter by about 30 degrees centigrade for every kilometre. That's a sort of ballpark figure that's typical of the continental crust, and it seems to be a reasonable value for the Humber region. As I say, places like Iceland, it's a much higher gradient. It gets much hotter much more quickly. Some places it gets hotter at a much slower rate. About 20, no, more than that, 30 years ago, I went to a gold mine in South Africa, and at 2 kilometers deep, it was quite warm at the surface, but at 2 kilometers, it was like hell. It was unbelievably hot, and so the deeper down you get, the hotter it gets, and you can use that heat to heat buildings. What we're looking for are rocks that have got open pores, and where those pores are filled with warm water. So the Sherwood Sandstone is an example of such a porous rock. but it can't just be porous. It's also got to be permeable. The water has to be able to move through that rock. So when we extract water out and pump water in, the hot water must be able to flow through the rock. And then we must extract the heat, bring the hot water up, extract the heat using a heat exchanger or a heat pump, and then re-inject it. So we're creating these loops of energy. I mentioned the Sherwood Sandstone. This is it's spectacularly poorly exposed in the study region. It does occur at the surface in the very west of the study area, but it's very badly exposed as far as I can work out. And I went to Seaton Crewe, which is in County Durham on the coast, and took some photographs. I wanted to make sure I'd seen the Sherwood Sandstone at least somewhere in the region before completing the project. And this is it. It's a reddish sandstone, not particularly coarse, but it's very porous. And the reason it's poorly exposed is probably because it is porous. It's very weakly cemented, and so it gets eroded fairly quickly. And this shows this is a bedding plane with ripples on it, and would have been a sand that was deposited and had ripple marks like you get on a beach or on a lake. And this is what the Sherwood Sandstone looks like. How old is the Sherwood Sandstone? Here's another exciting geology picture: dinosaurs. The Sherwood Sandstone is Triassic, and which is the kind of start of the age of the dinosaurs. And these are supposed to be Triassic dinosaurs. And this shows something a bit like what the environment would have been like during the deposition of the Sherwood Sandstone. So it's fairly arid, but with some lakes and rivers in it. It's a reddish color, which is typical of fairly tropical conditions or arid conditions. And so, yeah, I managed to shoehorn another geology picture in. Just another photograph of the Sherwood Sandstone. It's got these beds in it that are across here, and there are some fractures in it, but not much. You'd be mostly relying on the porosity and the permeability of the rock itself, rather than flow through fractures. So why do we think the Sherwood Sandstone is a good reservoir? Well, what I did just to make sure we got it right and we hadn't missed something. What I did is a qualitative analysis of the different potential reservoirs: the chalk, the Jurassic, mostly limestones, the Permian rocks, coal measures, etc. Deeper down you go. Of 10 different parameters, and this is part of the spreadsheet. So heat potential, I ranked each parameter out of 10, and so, for example, the chalk gave it a ranking of 10 out of 10 because we know it's across large part of the region, and because I had 10 parameters rating out of 10, you could add them together for each reservoir unit and get a kind of percentage effectively of favorability. And the result was this for the different potential reservoir units. The Sherwood Sandstone came out top because it's got usable temperatures, good quality reservoirs. There's a good seal unit above to keep the water in place. It's simple to drill. There's low environmental impact. There's good quality data, high certainty in the interpretation, and relatively low risk. Now, I mentioned the rocks get hotter the deeper you go, and so why not drill much deeper and get some of these really hot rocks? Well, the trouble is that there's much less certainty about it. There's much less data. The rocks might be hot, but maybe they're not so porous, not so permeable. And I know that at York, I've heard that at York they're drilling. They want to exploit the Carboniferous limestone, and I understand why they want to do it, but there's a lot of uncertainty with that. You're much less certain what the porosity permeability is going to be. It might be great, it might be terrible, but so there's an uncertainty there. With the Sherwood Sandstone, there's a high degree of certainty what you're going to get. There's a lot of well data, there's a lot of information, and we're pretty certain. So this is another cross section, and this is showing one of the cross sections of the British Geological Survey. I can't remember which area. I think it's just to the east of Hull. But what it's showing is a sequence of rocks, these sort of cover units, the chalk, Jurassic, this Mercia mudstone group, which is impermeable, forms a seal, this thick Sherwood Sandstone layer, some Permian rocks, and then down into the coal measures. So uncertainty increases with depth. With the Sherwood Sandstone, it's already been drilled at Scunthorpe General Hospital. There was a recent geothermal project there, and they achieved pretty good results. And it gave us much more confidence. But the project wasn't fully developed for fairly strange reasons. But they were happy with the results, and it could be successful, and that can be expanded across the Humber region. So the Sherwood Sandstone is pretty good. This is another cross section. I wanted to show this one because there's this well here, the Cleethorpes 1 well, which was drilled in the 1980s by the British Geological Survey, and it came out with some interesting results. It was drilled for geothermal potential partly, and what they found in the Sherwood Sandstone, the temperature there is roughly 50 degrees centigrade. It's a depth of about 1 kilometre to 1.5 kilometres, and it produces a flow rate at about 20 litres a second. Now that's not great, and I'll come back to the flow rates later, but it's just a single well. They didn't have an injector and an extractor well. And if you had an injector and an extractor well, you could bump up that flow rate. And there's other ways to increase the flow rate as well. So moving on to what I did for the favorability mapping, how to identify the best places. Well, I used public domain data. I learned a lot on AI and ChatGPT and Google Gemini to identify data sources and how to process it. It sort of sped things up a bit. Though, quite an interesting learning experience doing that. I used geospatial analysis to analyze and present the data, and the output was a favorability assessment of the region and of specific sites. And some of those specific sites are marked on here: Scunthorpe General Hospital, University of Hull, Trippitt Street, which is a district heating system being developed, and the Diana Princess of Wales Hospital in Grimsby. So collected some data, and how did I? Yes, why geographical information system? Why did I use this approach? Well, you're able with the geographical information system to integrate diverse data sets. Sorry, I think I skipped something. No, I didn't. Sorry. Okay, you're able to it's transparent and reproducible. If you tell people what you've done, what data you've used, and the steps you've taken, people can reproduce it, which is an important part of science. It's flexible. You can use different data sets and merge them. It's good for visualization. You produce maps. That's one of the key points of it. It's really useful for that. And it's easy to update. If new data sets become available, you can include them and improve the project. Now, I use this software called QGIS. The industry standard is something called ArcGIS, which is very expensive, really difficult to learn how to use. But QGIS is free, and there's an extensive community support. You can always find a YouTube video which explains how to do something, and you can just download it and use it on your home computer. So I use QGIS because it's simpler, and I produced a series of maps like this. This is a screenshot of the QGIS project, and what I did here was to divide the data into 10 classes. So in each class here, in each of these, there would be different data sets. So the geological ones are heat potential, reservoir presence, reservoir quality, seal integrity, stress alignment, how the stresses relate to known faults, and fluid recharge. Then there's drilling or ease of drilling. There's demand, environmental factors, and social sensitivity. And this map here is showing the building density. So there's a lot of good data, public domain data, that you can retrieve, put it into QGIS and analyze it. And what I did here is you can see how pixelated it is. These are 1 kilometre square grids, and the building density is picking out urban areas. So, for example, Hull, Driffield, Cleethorpes and Grimsby. I think this is Scunthorpe, and I think over here we're going into Sheffield, and no, this is Sheffield and this is Leeds, I think. But it's fairly simple to collect data like this and put it into QGIS. And these are the steps I took just fairly quickly. So find and import data. You've got to make sure that you're using the correct coordinate system. That's an important part of geospatial analysis. That's usually where the errors happen, where you're using mixing up different coordinate reference systems. Where necessary, you have to interpolate the data. So, for example, with building density, you can get that; it covers the whole region. You don't have to interpolate anything. But with wells, they're kind of fairly scattered across the area. So you have a data point from one location, data point from another location, series of data points. You have to interpolate between them. That's an area potential error. You find the value for each 1 kilometre square grid. You clip it to the region of interest. And the important step is to normalize the data. And so 1 is the most favorable, 0 is the least favorable. And why you do that is because with the different data sets, they've got different units. So there might be degrees centigrade for temperature, square meters per kilometer for building density. There's all these different parameters with different units. So if you normalize them, then you can compare them properly. You create what's called a geotiff, which is an image, which is an important step because you can use those geotiffs to merge them using different weightings. You can play around. I'll show you how I've done some of that later. But you create these geotiffs, these images, which you can then merge. And then once you've got the merge, you can normalize it to have 1 as the most favorable, 0 as the least favorable. Just to note that 0 doesn't mean there's no potential. 1 doesn't mean that the area is perfect. These are just relative potentials across the region. It's just a relative value. So the results. What I'll show you now is some favorability maps, an assessment of certainty, and how that can be used in site-specific analysis. So the favorability maps, here's an example of the heat potential. There's most heat potential in the east along the coast where the Sherwood Sandstone is deepest and therefore hottest. When you go into the west, the Sherwood Sandstone is very near the surface or at the surface, and so that's a fairly simple one. What I've done is merge the geological favorability ones together and got a map like this is the map I got. Again, it's most favorable in the east where the Sherwood Sandstone is deepest and warmest, and it's most favorable. These funny traces that you're getting, these are actually faults, and this is one of the things that is perhaps there's an uncertainty there that whether the fault. I think the assumption here is that the faults will increase fluid flow, so they're a benefit, and so they bump up the favorability a bit along and around faults. I know of cases where the faults are actually disastrous for geothermal energy. So, it does highlight the potential of using faults. I didn't just look at the geology, I looked at other factors as well. So this is a map of demand. So how did I get demand? Well, I used public data for gas use, and the gas use is a kind because gas is often used for heating, and that was a kind of better. We thought that was a sort of better proxy for demand than saying electricity usage, but the electricity use map is somewhat similar. But this again is picking out the main urban areas. So it's really showing that the demand is where the people are, where the factories are, where the government buildings, the hospitals. That's where they are. So it's fairly obvious, but gas demand shows that quite nicely. Environmental, what I did here, this is an example of how to merge different data sets. So I actually used several different proxies for environment, or several different environmental factors. So things like areas of outstanding natural beauty, SSSIs, conservation areas, source protection zones, brownfield sites, and heritage sites. So I used those, gave them an equal weighting just for simplicity, and those can go together to make a environmental map. I was a bit unsure how to add these together, whether to add them or to multiply them, because with environmental factors, things like source protection zones, should that just be sort of blended with the other things, or do you do what you do in risk analysis, where if something's got a high risk, you just kind of kill it for all the other things? And so what this is showing is that the area where there's source protection zones through here, through the Lincolnshire Wolds and the chalk up in towards Flamborough Head, that's a source protection zone for the chalk aquifer. Because it's a source protection for the for the chalk aquifer, should it kill geothermal in these regions? It probably not, because it's you can mitigate against it. It wouldn't be high risk for destroying the chalk aquifer. So what I ended up doing is just adding them like this, get a similar sort of map. And so, for example, Hull is degraded a bit because it's within that source protection zone. The kind of peak spots are these red squares here, and they're bumped up because of brownfield sites. But it's an example of how you can play with the data. One of the really important things with this analysis is that it's to get people thinking and talking. So I'm not claiming that the data sets I've used are perfect. I'm not claiming that the weightings I've used, the analytical methods I've used are perfect. It's open for debate, and it's to help people understand the process, and importantly, the uncertainty. So again, with the social sensitivity, this is really straying into areas that I know very little about. I use these 4 proxies with these weightings here: noise sensitivity, deprivation, population density, and Green Party vote, which I thought was quite clever. I'm not sure it's clever. I thought that was a measure of kind of public engagement in environmental issues, and I ended up with a map like this. And interestingly, the University of Hull comes out very lowest because it's noise sensitive and because it's an area that is not deprived. It's regarded as being a wealthy area, so it's it downgrades the university. As I say, these are really to this people to understand these issues and to get people discussing and debating. So finally, coming to the overall weightings that used. So these are the different parameters, these 10 parameters, 10 classes. These are the weightings I used, and ended up with this map. And that shows, as you'd expect, the most favourable areas are in the east, where the Sherwood Sandstone is the hottest and deepest, and in the areas, for example, around Grimsby and Cleethorpes, around Hull, where there is population. I was quite surprised actually that Scunthorpe came up very highly, but they've done a geothermal project there. They've looked at the Sherwood Sandstone as a geothermal reservoir there. I thought that, well, what I should do is to be honest about this analysis, and I on a scale of 1 to 5, I ranked the data quality. This is purely qualitative analysis of data quality and interpretation certainty. Now, the geology factors scored very low for data quality. These are quite poor compared to the surface data sets, but I'm pretty happy with most of the interpretations. The stress alignment, I'm not particularly happy with that one. The fluid recharge is, I think the data report and my certainty in the interpretation is very low. And similarly, well, not similarly, with the social sensitivity, that's really good data, but I've got very low confidence in my interpretation of those data sets. So that's again to give people an idea of the uncertainty in the analysis that I've done. So what we then did was with this favorability mapping, then took it a stage further to look at specific sites. And two of the sites that I looked at were the University of Hull and the Diana Princess Wales Hospital in Grimsby, where the NHS are very keen to have a geothermal well drilled. And so selected several sites for evaluation, collect the values from the QJS project, including the favorability maps, and this information enables these different sites to be ranked. And then also what I'll talk about in a bit is some of the data can be used to calculate the potential for heat production and some other factors which I'll mention. So with the site evaluation, these different sites here, I ran it through the QGIS project, got values for them. This is quite a big spreadsheet, and this is just a screenshot of part of the spreadsheet. We're able to collect lots of data, and then that enabled us to rank the different prospects. What comes out lowest is the University of Hull, sadly, and but that's probably because of the social sensitivity and the noise issues, the environmental social the social and environmental impact. The Yorkshire Energy Park comes out highly, but there's an important factor here, which is a sort of intangible thing. It's really the keenness of any group of people to develop a project. So, for example, if the University of Hull is really keen to develop geothermal, then great. If Yorkshire Energy Park isn't, then fine. So, but this is giving an idea of the relative ranking. If I had to select somewhere to drill, or one of these projects, which one would I pick? It would probably be the Yorkshire Energy Park. So, what this all means. Where have we got to? So the Sherwood Sandstone has good potential and very well constrained geology. The temperature increases with depth, but so does the uncertainty. So some of the deeper and hotter rocks, there's much higher risk involved. There are high potential areas around Hull, Grimsby, Hornchurch, and Maplethorpe along the coast. The weightings will affect the favorability, but the most important thing is going to be rock temperature and demand. These are going to kind of tend to override things. The fluid recharge model and the social sensitivity work probably needs more analysis. So that's where we got so far. But one thing I was struggling with is, well, what does this actually mean in terms of value? And so I really strayed. So I got into this and was looking at the kind of value. And so what I did use very simple equations, which I'm happy to discuss and share with people if they're interested. I used what I did is I modeled 4 different flow rates from the wells and 3 different reinjection temperatures for each of the study sites. So I ended up with this table here, and it's showing the heat that the heat extraction, it's estimate the heat extraction for these different flow rates and for these different reinjection temperatures. And so, for example, I got a value for this high flow rate and low reinjection temperature for the University of Hull, 7651 kilowatts. And I've got no idea what that means. I really can't picture what a kilowatt is. I did convert it into megawatts per year, but that didn't really help me either. So what I then did was thought, well, what would that mean in terms of savings from gas? Not a volume of gas, because again, I can't really picture that. But in terms of if you convert that gas using present day gas costs, but gas prices, how much savings in gas would you have a year? So again, taking this case here, 60 litres a second flow rate and 10 degrees centigrade reinjection temperature, it would save you 4.35 million pounds worth of gas, which is I was quite surprised by, quite shocked by. So, oh wow, okay, that's good. But then I remembered that to get this value, you need heat pumps, and you need to pump the pump the water through buildings at the University of Hull. And it turns out the electricity needed to do that, because electricity is expensive, would just about wipe out this value. So it's marginal economic value to do this, and it would take decades to recoup your losses, or your costs, I should say, at present day values. But there's other things in play. So I converted that into CO2 savings. If that gas you save, you're not creating CO2. How much CO2 would you save? And in this case here for the University of Hull, it'd be over 12,000 tons of CO2 a year that you're saving, pumping into the atmosphere. So okay, that's good. That's can be quite interesting. But it still doesn't solve the problem of the economics of it. And one of the things that's really important is not to look at geothermal energy in isolation. It should be part of an energy system, a renewable energy system. And so, for example, if you have solar and wind, you're using that, storing it maybe in power units to use for the heat extractor, the heat pumps, and for the pumps for the geothermal. Then it suddenly becomes a lot more economically viable if you're using when you create a geothermal project, if you install solar and wind, then you have a kind of independent energy system that would be potentially economically viable. So the keys to success, probably I put these by size in kind of how important they are for the Humber region. Well, in terms of what's needed for the future. So geology, the temperature and flow rate is important, but we know that that's good. Demand is important, we know that, and that's good. It's the economics are more important to work out the drilling, the plumbing, the maintenance, how much that costs. That's important to know. Integration is starting to become to things that this is really important to know. This is a key to success that's becoming kind of more important. To integrate it with other renewable energy systems. The political will and support, again, that's really critical. And a network of enthusiastic people is really important. And that seems to be developing in the Humber region. There are people that are really enthusiastic about renewable energy and geothermal. So hopefully something's going to happen in the next few years. And the huge project aims at getting people together to energy from being kind of a wish to a working system. So conclusions. Why does the Humber region need geothermal energy? Because there's a high demand and an urgent need to decarbonise. Might geothermal work in the Humber region? Well, yes, there's a lot of potential. Can we identify the best places for geothermal? Yes, the geothermal favorability mapping shows that the best places are where the Sherwood Sandstone is deepest and warmest, and where there's demand. What could geothermal energy achieve? So it can be really important for district heating and in regional decarbonisation. So it's important. So hopefully those are the questions answered. Yes, here's my email address. This is a permanent email address rather than a work email address. If you have any questions, if you have any comments, then you're very welcome to contact me. Hopefully this presentation was made available so you can find my email address, and I'm very happy for the Yorkshire Philosophical Society to give out my email address, and I'd welcome any discussion with people who are interested. Where may this lead? This is just something I thought I should show towards the end, which is a district heating system, a geothermal system in the Sherwood Sandstone at Southampton. Now, I did my PhD at Southampton around the time this was being developed, and I didn't even know about it. And now the Southampton district energy scheme has been running for decades, and it's just this inconspicuous warehouse. I don't think that tower behind is actually related to this geothermal scheme. It's just this inconspicuous warehouse. The most conspicuous thing about it is they painted it red, and I think that would be a lot less conspicuous, a lot less problematic than having, say, gas turbines or gas gas boilers that you would need currently at a hospital or a university to provide heating. Now, I've shown you volcanoes and dinosaurs. One exciting bit of geology now is earthquakes, and this is obviously Hull. So there's the Humber Bridge in the background, and well, that's not. It's probably Los Angeles or somewhere. But anyway, it's an action film that was produced of a major earthquake. Why is this relevant? Why am I including this rather than just a feeble attempt to make it seem exciting? Well, one way to increase geothermal output is to enhance the rocks. You can increase the porosity. You can you can cool the rocks and cause cracks in them that might increase flow. You might put acids down them to dissolve minerals and then increase the flow, or you might frack it. And when I first started working on geothermal on a project in Germany, I asked them, would you consider fracking it? And they looked horrified and said, no, we can't possibly do that. It's against the law. And if we accidentally cause an earthquake, the project would be dead. And so, oh, okay. But then I learned more recently. Oh, it was illegal apparently in the European Union to do fracking. But I've learned more recently that apparently there's for geothermal, at least in Britain, there's kind of sympathy for it. That even people like the Green Party, I understand, are kind of they're not against it, as long as you're not causing something like this. Um, if you have some very minor earthquakes that people can't feel, then people are okay with that if it's for geothermal energy. So yeah, there is a future for geothermal energy, and perhaps even a role of fracking in that. So that's the end of the presentation. If you have any questions, then I hope you're able to hear me all the way through. If you have any questions, then I'll willingly take them now.
Thank you, David. Thank you. Um, may I just check about the favorability map? Did it include a range of base rocks, or was it only the favorability map built on the assumption that it was going to be Sherwood?
Yeah, it was just the Sherwood Sandstone. I could do other
Yeah,
was the focus of the project. Because well, we started off by thinking it's simpler and we know that it's a reservoir, so we did that, and then I thought, well, I should look at the other reservoir units, but the same approach could be used for the other reservoirs. Oh, one thing to mention as well is one thing I learned in Germany is that there is a potential role for using multiple reservoir units, different temperatures. You can, if you have an integrated geothermal system using different reservoir units, then there are some advantages to that. But it makes it quite a lot more complicated to uh, to make a system like that.
right. Thank you. There is one question in the chat already about using using this geothermal hot water for new build housing estates, perhaps in Hull. Obviously, it's difficult to re-engineer every individual house, as you pointed out, but there are some estates built with a centralized boiler system. I think Derwentthorpe has it here in York. Is there any? Would you think there would be interest in doing this for new buildings?
Yeah, I think so, and also if you do have an existing district heat network, I actually did manage to find a government map of existing district heating networks, and there's a few around, and there's one that's being built in Trippett Street in Hull, and so there's a lot of potential for that. For um, so it could be a housing estate, it could be a hospital or a university. So apparently at the university, at the Diana Princess Wales Hospital in Grimsby, they have gas boilers there. So they've got a central gas boiler, which is or boilers which are being used to provide energy for the district heat network. And those boilers have, I think he was telling me that they have a life of 20 years. The trouble is they're 40 years old, and they need to replace them, and that's why they're seriously looking at geothermal to replace the existing gas boilers there. So it would work in any system like that. It could be a new building. Well, I think so. So around Grimsby, the hospital in Grimsby, there is what I take to be an old council estate, and if it was still a council estate, there would probably be a much easier to fit it with a district heat network. I think the problem would come is if a lot of those houses have been sold off, you'd have to have the
Yes.
approval of all of the homeowners. It becomes very difficult. But so that's why, for example, a new build housing estate would be ideal for it. It's whether the developers will be prepared to take the punt on that to do it. I I think the trouble is that well, they're sort of straying into politics a bit, but with things like oil and gas, people can kind of picture it, and that there are big corporations with a lot of money that are prepared to invest in that, and they know they can make a profit from it. With geothermal, far fewer people have done it. The technology is much less certain. People are less familiar with it, and I think what it needs is some people to invest in it, take the risk, and when the risk pays off, other people will jump on it. But at the moment, we're kind of on a tipping point in Britain that some people are doing it. There's a lot of interest, but we need more people to actually go ahead with it. The Eden project in Cornwall is a case where it's been done successfully, and we need more. Well, Southampton as well, but we need more people to take the punt. So if someone is doing a new build housing estate, they can include geothermal, and that could be a selling point. It could be cheap green energy for the homeowners or occupiers. So yes, I think new build housing is a very good idea. Yeah.
Mm. You mentioned in the ranking that the Yorkshire Energy Park Phase 1 came out high. What's the demand there? What you'll have
Oh,
to.
sorry, you're back again. Sorry, yes. I mentioned the ranking.
Sorry, you mentioned the rankings. You had the Yorkshire Energy Park Phase 1 came out top of the rankings, and I'm just wondering what they do and what's the demand. I mean, is there social stuff coming through?
I think it's my understanding. I don't know a lot about it, but I think it's part of the Freeport scheme. So as part of the Freeport scheme, they decided they were going to have an energy park that would, I think, be looking at renewables as part of the mix. And I think it's my understanding that they're mostly focusing so far on solar and wind. And so we're in the process of organising a meeting and contacting people to attend the meeting, and so we can, well, it'd be a workshop so we can debate the geothermal and the role of geothermal. So hopefully the people there will come along and discuss their work. And as far as I'm aware, they're not into geothermal at the moment, but it should be part of the mix there.
Right. Yeah. Yeah. And there's another question. I'll have to ask Catherine whether there are some coming through on the chat directly to her, but I've just seen the ones for everyone. And there's a question about expanding. Are you able to get people round the country to expand your work? So to stimulate more interest.
Yes. Definitely. What I'm hoping to do is to publish this methodology and show people how it's done. And it's fairly simple and straightforward to do it. And I had used QJS before, but I was not really an expert. I'm still not really an expert on it, but I'm showing a methodology that people could use for the assessment, and I hope to publish it so people can use it. And it would certainly expand itself to the rest of the country and to different reservoir rocks as well. So if you wanted to look at the Carboniferous limestone, you can do the same thing. Indeed, a lot of the data I've got, or the social aspects of it, and national data anyway. So it would just be a question of using the local geology in that. But yes, it is expandable. I hope that people will use this.
Um, just, Catherine, is there anything coming through on the chat directly to you rather than
No,
to anyone?
just on the general one.
Okay, fine, fine. So, are there firms that would be interested in taking this up and actually, or is it just Hull just involved in qualitative at the moment? Does it have links
Well,
within?
we do have. Yeah, and that's part of this project is to help create a network of people who are interested, and we want to give the results of this work to other people. So, for example, I've been in discussions with the energy manager of the NHS in the region anyway, at least part of the region. Very helpful guy, very friendly, and I've given him the results. We discussed them. They wanted to drill at Grimsby, and the results that I've shown him sort of give him a lot more confidence that Grimsby would work. And but there are other people as well that we want to get involved, and we're hoping to have a meeting. There was one plan that we were going to have a meeting on the 17th of September where we're going to invite people, but there's another group, a company I think, who are organising a similar meeting for 6 days earlier. So I think the 11th of the 10th of September, and so it's right. So rather than have it so soon after theirs, we're going to delay it a bit. We're talking with them at the moment about thing because we're a university. We're not really interested in how do I put this? It's not a kind of proprietary, secretive bit of work. We hope that other people are going to be able to use this, and we're very happy to cooperate with other people. There's a question about agriculture and yeah, greenhouses in Iceland. That's one of the things that I hadn't thought about until a friend of mine mentioned it about greenhouses. There's quite a lot of greenhouses in the region. And that does change it a bit. That you could have I know, for example, between Hull and Beverley there's a lot of greenhouses, and it does lend itself for that. And I think in that case you probably wouldn't even need heat exchangers. You could just pump the water through, and it would work very nicely. So yes, it is. One of the layers I have as well is building type, and I managed to get a map of different types of building, and I took out things that could be kind of relevant, like breweries, retail centres, prisons, and greenhouses. Greenhouses is another one. So I've got a map of these different types of building where it might lend itself. But certainly greenhouses it would definitely lend itself to that.
Presumably, you don't want to pump this water too far. So, how sensible is it to have a borehole for each area of greenhouse, each business that has greenhouses?
Well, yeah, this is getting into things. Strangely, I've been thinking about this quite a bit actually, because my father was a heating engineer, and then my brother became a heating engineer, and so they would have been able to answer this. And I'm not a heating engineer, so it's getting into the surface. That some of the surface stuff is kind of is stretching my knowledge. Unfortunately, ability in heating engineering doesn't really it's not genetic. So it's I think the idea is that you wouldn't really pump it like a kilometer or so. It would be a few hundred meters. And so what you would need would be ideally a sort of a certain area where a high density of, in this case, greenhouses, and you would have a couple of wells there, an injector well, an extractor well, and a district heating system for that area. But you would presume, I think someone mentions it here, that you would need other heat pumps. You could have a whole series of heat pumps. But I think then the economics start getting a bit difficult if you have a string of heat pumps, the economics change. Ideally, you would have injectors and extractors supplying just a local area.
Yes, yes. And following up, there's this other comment. The question: Are you're developing a methodology which is going to be a tool which people could use for, as it says, a cost-benefit assessment analysis for different sites, so they could decide whether
Yeah,
their area is or isn't suitable.
yeah. One of the project partners is Eden Geothermal, and they've got a lot more experience in this than me. And so my aim was to do the favorability mapping and um, to show the areas that are most favorable, and to the risking and ranking. And then the idea is to have the Eden Geothermal to do kind of much more detailed site specific analysis. The analysis I did, the economics are very rough and ready,
Mm.
and I'm very happy to share that with people so they can do an estimate themselves. I, in terms of confidence, of one very low confidence, five very high confidence, I'll give it a one or a two for the work I've done, because it's very basic. But hopefully Eden will be able to produce something a lot better. There might be commercial sensitivity in it though, so
Yes, yes,
that could be a problem. I'm happy to. The work I've done, I'm very happy to share it with people. If someone wants to email me, can you share that with me? Yeah, sure, fine. I'll be very happy for people to see it. 'Cause, I'm academic, so there's no commercial sensitivity to it.
yes, yes,
The stuff Eden do, there might be a commercial sense.
yeah. And the important thing being that with this, you'd have to make sure that the extra electricity involved in
I've
pumping.
lost you. Ah,
Oh, sorry. Yes, you're been blinking in and out sometimes. Are you back with us?
yes, I can hear you again.
Okay,
Yes,
fine.
I can hear
Yeah,
you now.
yeah. So they've got to be sure that the extra cost of electricity involved in all this pumping isn't going to outweigh any economic benefit. Because
Yes,
I mean, green's important, and transitioning to a green economy is good. But if people are going to make a loss, they're probably not going to do it.
one thing, and another factor that could be important is that the if you did have a system like that, that you have wind turbine, solar panels, that's using generating electricity that you could use for the geothermal. It gives you a protection. It gives a buffer against fluctuations in the energy market. Now, it could be that the price of gas just plummets, and then you think, why did I do this? But it could be that they raise dramatically. And if you're a hospital trust, or a university, having that certainty could be extremely important. It enables you to budget. So there could be benefits like that. Um, yeah. So there's a question here about Icelandic academic work on geothermal that could be used. Yeah, I mean the Iceland. Yeah, there's published information on that. One thing is that there's quite a different geothermal system because mostly they're generating electricity,
Mm.
and so there might be other places where they're using heat that could be more directly useful. So there are a few in Europe as well, I think, that could be used. So yeah, that's something that could be done as sort of wider study of other geothermal projects, comparison with existing geothermal projects. Oh yeah, someone's written here.
Storing heat.
Oh yeah,
Can it store heat the way you can store electricity in
heat can be
batteries?
stored. Yeah, yeah, and I think I mentioned this that I think I mentioned it that you can if I didn't if I didn't I should have done. That one thing that you could do with geothermal is not just use it for heat, but you can use it for cooling as well. If you reverse the heat pumps, that you can and the recent heat wave shows perhaps the need for this in Britain that you could have cooling in buildings in the summer, and the heat you extract you can store underground because heat storage is relatively cheap. But if you have a geothermal system, you can store that heat underground. You can heat the water in the summer and extract that heat in the winter. So if I didn't mention that, I apologise because I meant to.
Mm.
So yes, heat storage, and that you can actually store it on the surface as well. But the storing it underground might be a kind of more elegant solution.
Mm. Perhaps just as one last question, in your favorability map, it looked as though you had some red dots to the northwest of your region. Was that heading towards York?
Let me see if I can. I'll dig it up and share it. Hmm. Share screen. And there. Oh yeah. So these ones up here.
Yes, yes.
Yeah. So yeah, this is actually quite interesting because this is the Flamborough Head fault zone or Flamborough fault zone, I think
Oh,
it's
yes.
called. And before the talk, just when we were talking earlier, I mentioned that Flamborough Head's really good. It's a great place for a field trip. There's actually
Yeah.
south coast here, a lot of small faults, but through Selwick's Bay, there's a fault, Selwick's Bay fault, but it connects to this fault zone that goes all the way across here, and it connects to the west. Is it the Craven Fault? I'm not sure. I can't remember. There's a fault system to the west that's in the Pennines,
Yes,
an
yes, the
east-west
Craven.
fault,
Yeah, yeah, the
and
Craven.
and then it also it connects to this thing that goes down through the southern North Sea called the Dowsing Fault, and it certainly affects the chalk. So it's got relatively recent activity, and the reason these dots are there is because, this is somewhat problematic. This is something I'd rate as a low certainty. That this fault zone, this Flamborough Head fault zone, particularly if you look at the orientations of the stresses in relation to that, there could be dilation on those faults, or there could be fluid flow along and around those faults. And if you go to the right at the tip of Flamborough Head, you get one of these fault zones, and there's a lot of calcite there. This Selwick's Bay fault zone. There's a lot of calcite along this fault, and it shows there's been a lot of fluid flow along there. And so it shows that there is potential for fluid flow along these faults. The trouble is, and this is where the problem lies, is that It could be there's been so much fluid flow along these faults that they're all mineralized. They've all got loads of calcite on them, and there's very low porosity and
Yes.
permeability along and around these faults. So these could be good, or these could be really bad. So there's a bit of there's an uncertainty there. But that's why these red dots are here. The same down here. There's a mapped fault that goes through this area, and it could be that it's great or it could be that it's terrible.
Okay. Yeah. So more work to refine these this thing.
Yes.
Well,
Yeah. And it'd be very easy to change this. So what one could do, for example, is to color code this differently, to invert this color code so that where there's a fault, it's given a very low grading,
yeah,
and for the reservoir quality, and you say no, it's poor there, so you just change it around. Here, the assumption is that it increases reservoir quality, improves reservoir quality.
it's the faulting up there in the that's right.
Yes. Yeah.
Yes. Yeah. Well, thank you very much. I think we've taken a lot of your time, and and I think you've gone through your all the points you wanted to raise very thoroughly. Let's hope it goes further and people want to take it up, and look forward to hearing about geothermal energy in Humber and in the Humber in future.
Yes. Well, thank you.